Welcome to statistics. We're going to look at confidence intervals today. So the idea that we want to get across here is how and what can we do with these numbers and all this data that we collect. And one of the things that we need to make sure is that it is somehow useful to us. So one of the things that we're really looking at is how do we infer or how do we to figure out things about the data that allow us to make decisions down the road or give us more insight into the data set that we now have in front of us. Okay, so let's jump in and see what we can talk about here. So the first thing is when we talk about statistics is we have this inference thing, which simply means that we have methods for drawing conclusions about whatever population we're looking at based on the sample. Okay, so the idea here is that we're going to use confidence intervals is one way that we can go about figuring out a little bit more about the data set. Okay, now for us to use these confidence intervals, there are a few things, and this is kind of true about statistics in general, and I'm going to talk a little bit about some of these points as we run through this, because in some cases people, a lot of times with statistics, they're like, well, you can just really do that? And the answer is yes to some of those statements, and we're going to kind of work through that. So first of all, we have a simple random sample, which just simply means that we've collected data on a random basis. Now, if we've gone out and only selected a particular group and we very much engineered, well, then that's just bad data collection. So the idea here is that we're collecting the data as best as we possibly can, and we're kind of making the assumption that we're going to make it a simple random sample, and that random sample is going to be the best data collection we can make. Now, the caveat here, or maybe a warning, is that when we deal with a population or a subgroup of some sort, we might see some skewness in one direction or another because we are inside of a subgroup. So that is one of the reasons why when we talk about a simple random sample, we're not necessarily talking about subgroups, although subgroups may fall into line with this as well. You just need to be a little bit more mindful when you deal with them. The other piece of this that is really important is, or another piece, is that there are no non-responses or other practical difficulties. If you've sent out, you've done a survey and you've collected some data from the survey, and half of your responses are not completed. So you've randomly selected 1,000 people or 500 people to partake of this survey, and you only get half of them back. That is actually a problem with your data set because half your population has not responded. So what do you do with that? Then there are means of ways we can deal with that. If you've done this via email, you send follow-up emails, you put some type of incentive in there. There are also ways of emailing on the front end and then emailing the actual survey and then doing a follow-up email and then doing a tertiary email as well. If you're doing this via phone call or knock on the door, you go back multiple times. The idea is to make the best faith effort to collect as much of that data set as you possibly can. And there are thresholds that have to be met sometimes. And we can talk in other videos, we'll talk about some of those thresholds. The population is large compared to the sample size. So if you are sampling 500 people and you have 600 people in the population that you are sampling, that is not going to fit. Okay, so that does not meet the simple conditions here that we're talking about. It needs to be large. So we're going to look at a population that is 20 million large, and our sample size is going to be 500. Okay. That's actually a great deal of data for us. If we are randomly selecting our data, that is actually probably plenty for us to get good data measurements out of. And also we're going to assume the idea that the data is normally distributed. We don't know the mean, but we do know the standard deviation. And here's the part of this stuff that people are like, you can really just do that. You can assume the data to be normal, and you can automatically know the population or the standard deviation of the population. Notice the wording there. It's the population standard deviation, not the sample. So we're talking about that we actually know the value of a parameter, not a statistic. We're saying we know the value of the parameter, and we talked about in other videos how you don't know that value. So what we're actually going to do here sometimes is we're going to assume the value for the parameter We're going to assign the value, if you will. And what ends up happening is when you do that correctly, you actually get this to work out. It's actually kind of weird the way that it does work out. So you're like, well, how can you just go through and do that process? What is interesting is the fact is that you can just go through and do that process. It's an interesting attribute, if you will, of the statistical process here. Okay, but the mean we don't know. So that's kind of an interesting thing to deal with. Now, as far as the normal distribution, you'd graph it in a histogram or some other type of maybe a stem and leaf plot, and you'd get the idea that it was mostly normally distributed and not really skewed, and that'd be enough, really. So an example. So this is a report on BMI, and before I actually get into the data set here or talking about what's going on here with this example, I just want to make a disclaimer that BMI is body mass index, and that is a indicator used by health organizations and the medical community to classify overall health of an individual. BMI can be collected a number of different ways. The simplest one is height to weight as a ratio, and it kind of correlates to a particular number. And I will say that this is a personal disclaimer. When collected like that, I think that BMI is a horrible indicator of overall health. And I'll use myself as an example of that. I am broad-shouldered, and I'm not terribly tall, but I do have a waist that is sitting right around 35, 36 inches, which for my height, for a man, that is right at the good health level. Ideally, it would be a little bit slimmer than that, but who wouldn't, right? But overall, that is a good indicator. But because of my larger than normal muscle mass, my BMI is actually extremely high in comparison. So I actually had a doctor looking at me and tell me that I was morbidly obese based upon my muscle mass. That's not a good indicator of health. So I just wanted to throw that disclaimer out there when there are multiple ways to determine body mass index, and some of those, the more strenuous versions of that include measuring your wrist and your arm size and your neck size and your waist size and a couple other measurements, and kind of comparing all those numbers. And that gives you a much better indicator of your proper BMI as a comparison, rather than just looking at height and weight. So just keep that piece in mind. So if you go and you go to a website and you find your BMI and you're like, oh, that means I'm unhealthy, well, double check the values. Also, the other direction is true as well. You might go there and you say, oh, my BMI says I am healthy, and it's like it can also go the other direction with that as well. You need to be quite careful when you look at those values. All right, so back to the statistical discussion here, away from that momentary Dr. Kuhn disclaimer piece. Okay, so here we have an N value of 654, which is the number of people that were in the sample. Okay, that's our sample size. And the particular subgroup we're talking about is 20 to 29-year-olds. And the idea is that there is an assumption that these individuals were randomly selected. And this is of a much larger group, say 21 million women in the United States that fit into this age bracket here. And the thing is, and we're going to look at this in a little bit, is we don't need to collect all the data. All right. What we find is that the values are pretty close and pretty accurate as is with this piece. So when we look at this, we have a mean of 26.8, which we're going to assume to be our mu value. We had a standard deviation of 7.5, and I'm actually going to look at another example here in a moment that kind of gets us another, kind of gives us more insight into where that value can come from. For right now, I just want us to assume the standard deviation for the population would be that 7.5 there. We're going to use that. And we want to just kind of assume a normal distribution. This allows us to assume these simple conditions, which allows us to be able to do this confidence interval the right way. Now, a couple other little pieces to remember the 68, 95, 99 rule about a bell curve. about a normal distribution, meaning that one standard deviation, you're in either direction, you're including roughly 68% of the data. Two standard deviations out from the mean, you're including 95% of the data, and three standard deviations out, you're including 99.7% of the data. So that's that piece. So what we're looking at here is if we go one standard deviation in either direction, all right, this is going to create for us, actually goes two standard deviations, go two standard deviations in either direction. This is going to create a 95% confidence interval, meaning that 95% of the data, or we would assume that 95% of the data would fit into that realm. So in this particular instance, with a mean of 26.8 and a standard deviation of 7.5 and an n value or a sample size of 654, we end up with that standard deviation piece, or that actually what that is a margin of error. Shouldn't be SD there, it should be a margin of error is 0.03 in this instance. We add and subtract that to mu, our mean, and that gives us the overall value. And we're like, well, those numbers don't match up. That's not plus or minus 0.3, it's plus or minus 0.03 times 2, and that's that value we end up with there. Okay, I might have a decimal off there. That's supposed to be 0.3, not 0.03. All right, so now when we say a level C confidence interval, that C is that 68%, 90%, 95%, 99%. That's what that C is. That's just kind of a variable, if you will, for how confident we want to be in this. And in some cases, it kind of works backwards in where you may think it should. But the idea here is that we're going to take our estimated mean and we're going to add and subtract to that our margin of error. And this gives us the probability of capturing the true parameter within those bounds there. Okay, meaning that the actual mean, on that previous example, that actual mean, if I go back a page, is where 95% the actual mean is between 26.2 and 27.4. Okay, that's where we would assume the actual mean to be, is somewhere in there. We're 95% sure that it is in that realm. Okay, this is not guaranteed the mean is actually in that interval. Okay, so I created a graph here. If we were to go ahead and reproduce this study multiple times over, the black line, the black vertical line, there represents, say, the 20, the actual mean of 22, whatever it was on the previous slide. Each of those blue lines represents a 95% confidence interval for different groups. Notice that it is actually possible for the mean to be completely outside the realm of some of the other of the actual interval there. So if we were to think about this interval right here, spanning from right there, spanning from right about here, right where the bell curve starts to flatten out to the other spot, that'd be about 95% confidence interval. And these arrows are indicate the end of that. We're talking about there's a possibility that the mean is completely outside the realm of that actual 95% confidence interval. Remember, this is a probability, which simply means that it is likely in there. We're 95% likely that it's going to be in that realm. It's not a 100% possibility. Okay. Now, how do you figure this, or how can we do this even better? One way is to think of this in terms of a standard normal scale. Okay, so instead of just looking at this in terms of two standard deviations over, think of this in terms of standard normal, where you're actually going and figuring up a z-value. So if you have a 95% confidence interval, you can figure out the z-value that corresponds to that. And there are two ways you can do this. And the big reason you'd want to do this, it gives you a more accurate confidence interval. The other one is completely acceptable, but this gives you a more accurate version of that. Okay, so instead of doing 2 times sigma over square root of n, we would do 1.96, and this would be a 95% confidence interval. Now you're like, how does that work? So if you go on your chart here, this is actually a z-table, standard normal curve table here, and you find 95%. Now, if that's the realm you decide to go with this. Now you look around, you look for 0.95. Oh, this is 0.95, this is 0.950, so it might be a little bit closer, so maybe somewhere in between there. Right? If you look straight across from there, there's 1.6, right? And if you look straight up from there, you get 0.04 and 0.05, which means you're talking about 1.645 would be kind of in between those two places. But that's not the number I have there for Z. If you look at the number I have there for Z, you look right here, there's 1.9, and here's the column for 606, so that's 0.975. How does that match up? How does 0.975? I wanted a 95% confidence interval. Yes, because I want 2%, 2.5% outside on either end of this confidence interval. It's not a one-sided piece, it's a two-sided piece, so I'm finding the middle piece. So 95% of the middle, not 95% of one end. So 2.5% from one end. So this is 2.5. 0.975 is 2.5% from one end of this, and that lines up with 1.96 as the Z value, okay? Another way you can do the Z value, you can also use programs that figure this for you up as well. But another way to do this is using a distribution table. Notice the little graph up there. I tried to make sure I included that in there. You're actually talking about those little tails there, right? That's the piece you're wanting. You're wanting what's in between those two pieces of the tail there. So you look down here at the very bottom of this one. You notice you have all these values like degrees of freedom. This is your value for n, by the way. N is the degrees of freedom, or the number of your n value minus 1 is your degrees of freedom. So if you had 101 or 1,001 responses, your degrees of freedom would be 1,000. Here we're just talking about Z, just your plain Z value, and that's just an approximation that we can use. And notice you got 1.960. You look straight up from there, there's the 95% confidence interval for us. You can go 96, 98, 99, all the way up to 99.9. And then you go the other direction, you do 50. Notice the value is even smaller. That's going to be important for you to remember that as you look across this scale here. You go from 0.6 all the way up to 3.2 there, 3.3-ish, right? Right here in the middle of 95%, that's 0.1 or 1.96 is the value that we're going to be using. That's where that value came from. So now you can refigure this using Z of 1.96 instead of just 2 standard deviations over, like we did on the other version of that, and it's fine to use 2 standard deviations. This gives you a slightly more accurate version of that same data. Now I just want to kind of go through this in a little bit more detail just so you have an idea of where all these different pieces come from. So what I did was, here's another example for us to look at. And I just took this data set and I plugged it into Excel, and I had Excel create the mean for me and the standard deviation. Okay, so this particular data set was looking at, there are 20 pieces in the data, and the numbers you see there in column A represent the percentage of tip that was left by patrons who visit a restaurant, and on the ticket was listed tomorrow's forecast is going to be sunny or some other type of nice weather event, right? So the weather on the ticket told people the weather is going to be nicer the next day. And these are the results for that to occur, okay, for tips wise. And what we found, if you look there, the mean is 22.21, and that's the value for the mean I'm using right there. And then the Z value of 1.96, so 22.21 is the X bar value. 1.96 is Z. The standard deviation of 2. You remember I told you we're just going to assume that value to be 2. We did it again here as well. Notice over here it actually figured the standard deviation to be 1.96. So if you want to be a little bit more accurate with this, you could use 1.96. But 1.96 averages to 2, so that's actually pretty close to as accurate as we need it to be. And then we're just looking at 20 pieces of data here. And that tells us that between 21.33 to 23.09 is the tip. We're 95% sure that the average tip is going to be between 21.3 and 23.1% on top of the restaurant ticket amount. Okay, so that's what that means. Now the next stage of this would be to sit down and say, okay, so let's compare that to tickets that say had nothing on there whatsoever, or had tomorrow's weather is going to be cloudy and rainy, which a lot of people associate as being bad weather. I personally think that all weather is weather, so why are you calling one bad or good? At some point, I guess we were taught that rain was bad, even though it makes everything grow. Anyway, so what else can we do with this? Well, let's just kind of do a comparison here. So let's just say that for stormy and rainy the next day on the ticket, that got us 21.45 to 22.95 with a mean of 21.7. So, and keep in mind that second bullet point there is just made up. That's not actually part of this data set. I made that up for comparison. So the blue line represents good weather in the average and the 95% confidence interval for there being good weather the next day, and the tip amount, and the green line represents the 95% confidence interval for stormy weather the next day. I just made that green line up, okay? And that's not real data. When we look at this, can we really determine just based on the means that there's a difference? Well, it looks like 22 versus 21, is 1% going to make a big difference? If you're talking about a $40 ticket, you're talking about 1% difference. You're talking about cents at that point. $40, you move the decimal point over 2 places, that's 40 cents difference. That can add up over the course of an 8-hour shift, but we're not talking about a whole lot of money there. But is it statistically significant? Well, we can look at the interval, and that gives us a much better range. So we're 95% sure that the value is somewhere between 20.45 and 22.95. So the upper end is different, the lower end is different. So overall, it looks like according to this, that the blue line is going to indicate that the tip amount will be larger on average than it would be if the weather is indicated to be stormy the next day. Okay, so that's how this is useful to us, or one of the ways this is useful to us, because now we can actually look at that, because otherwise the values themselves, just the numbers, aren't necessarily a big deal. The averages aren't hugely off. But when you start getting into the confidence intervals themselves, the confidence interval for the blue line is much more compact, which means that we have a much better idea of what's really going to happen. So the green line implies that there may be a little bit more variability in this. Now, if we were to do this and we were to find the green line was ranging between 18 and 20, well, that's a really good indicator that there's a difference between those two things, because there's not even any overlap. So that's the way that those little pieces are useful, and how we can use them to make decisions and inform what we know about a particular situation. Okay, and then if you really wanted to get me going off on a tangent, is should we even be tipping at all? Shouldn't that just be someone's paycheck? But anyway, no one asked me that. So, margin of error. Right? So when we talk about a margin of error, that is what z times sigma over the square root of n is. Okay, that is margin of error. That's how much we think we're off by, okay, or that we could be off by. We can make this margin of error smaller in a number of different ways. First way is to get z to be smaller. Now, when we say z is smaller, that means that we're reducing our confidence interval, meaning instead of being 95% confident, we're going to be 68% confident or 50% confident. And then that's going to make that value of c smaller. Okay, remember the table I showed you. The larger the confidence, the more accurate, we want to include 99% of the data. Well, that means that z is going to get bigger, which means our margin of error is going to be bigger because we're including more and more of the data, right? Next piece is that standard deviation is smaller, will reduce the margin of error. And the only way to do this is actually to reduce the amount of noise in the data set. And another way to look at this is outliers that we might have, things that just don't make sense inside the data set. And when you start doing things like that, you start bringing into the possibility of questionable practices and also a lot of other pieces that go into that. But there are legitimate ways to reduce the noise out of a data set. Another way to do this, and this is probably the best way to do this, is to make n larger. Now look at the equation or the expression we have for margin of error. Z is a numerator, sigma is a numerator, n is a denominator. The larger n gets, the smaller the margin of error gets. And we can directly control the size of n. So if we think about setting up a situation where we want the same margin of same interval, the same confidence interval, say 95% confidence interval, which means that z is equal to 1.96. We're going to assign sigma to be 2 standard deviations, or 2 is our value for sigma. And then the mean, or mu, or x bar, whatever, however we want to assign that, is going to be 22.21. Now, if we let n equal 40, we plug 40 in there, and we get our confidence interval will be 21.5 versus 22.8. So we know that 95%, we're 95% confident that the average, the actual mean, is somewhere in between 21.5 and 22.8. If we go ahead and increase our sample size from 40 to 400, now all of a sudden we have 95% confidence that our actual mean is somewhere between 22.01 and 22.0 or 22.4. So we're only talking at that point of 4/10, almost not even quite 4/10, but 4/10 of a difference between the end and the beginning of the interval, which is a much more compact interval. Okay, so our margin of error has to be smaller. If we take n all the way up to 4,000, at that point we're talking about it being only off by 3/1000ths, or probably 3/100ths of a piece here, okay, which is a tiny interval. If we're talking about this being BMI, 40 is probably good enough. When you stop and think about that, you're not even talking a full 1 unit off at that point. You're talking 0.7 or 7/10 off inside the interval. Not 7/10, I'm sorry. 1.3 off from the beginning to the interval. If you take that up to 400, you're taking that off to be just 4/10 of a difference between the highest and the lowest spot. That, as in terms of BMI, is a pretty solid range because you're not going to see a whole lot of variation. 22 is 22. If you're talking about this being tip amount, you're really in a solid realm when you're talking about 22 to 22. So there's not that need to go to 4,000 because you're not going to be making any increase in usable accuracy at that point for BMI or tips at that point, percentage of tips at that point. Are there situations where that could be important? Yes, there absolutely are, where we might want to go in that realm. But most of the time, 400 or sometimes even 40 is really all we need. Okay, so just keep that in mind. And it may seem weird, like, oh, we can get all the information we need just out of a small data set. We really can if we have properly discovered the value for our sigma and for our mean. If we've done that as a random sample, we should be pretty well set up. All right, just about done here. When we talk about margin of error, z times sigma divided by the square root of n is our margin of error. And as I said before, we can make the margin of error smaller by letting z get smaller, which means you have a smaller confidence interval. You can also make it a larger interval by making z bigger. And I encourage you to go through, just like I did with the values of n, I encourage you to go back through and address the different values of C with 90, 95, and 99%. Go back to that table that I have listed on one of the previous slides. I think it was slide 8. And you can even find that on, if you were to Google it, you can find it that way as well. They will produce different intervals. And you'll notice that the interval for 90% is going to be a smaller width than the interval for 99%. 99% is going to include more possibilities, so it's going to be a wider interval. So try that, play around with those values, and just kind of dig in a little bit and try it out for yourselves. I hope this is useful. I hope you find something in here that has intrigued you, that makes you want to dig deeper into mathematics and statistics. Remember that math and statistics are ways that we answer questions and phenomena that we see around our world every day. It's not really meant to be some of these processes that you're meant to just memorize. There are, of course, that does exist. But these are meant to be ways that we answer questions and phenomenon that we see in our world. So always approach this from the lens of, what can I do with this information, and how can it be useful? All right. So I hope you enjoyed this. Take care.